Welcome to this explainer. Today we are looking at something just truly fascinating. We're going to explore how a tiny, seemingly insignificant piece of metal dictates the immense, overwhelming forces of an entire oil field. It is an absolute masterclass in mechanical elegance, and honestly, by the end of this, you will never look at a simple pipe the exact same way again. Okay, let's dive right into this. I want you to picture two pipes sitting side by side. From the outside, they look absolutely identical. If you push fluid through both of them from left to right, they behave exactly the same way. The fluid just flows right through. But here is the mystery. The moment you reverse the flow, one pipe lets that fluid travel straight back, while the other pipe stops it dead in its tracks, no way through. So what on earth is going on inside that second pipe to create such a drastically different outcome? Well, the answer is deceptively simple, and it's hiding right there inside the pipe. The only difference between the two is a single, polished steel ball, about the size of a marble, sitting on a machined ring. That one part, that single steel sphere, is literally all that decides which way millions of gallons of fluid can travel across an entire oil field. So what we're actually looking at here is called a ball and seat valve. It's essentially a one-way check valve, and its beauty really lies in its utter simplicity. It consists of just two working parts. First, you've got the polished sphere, which we call the ball, and second, you have the matching machined ring, which is the seat. That's it. There are no motors, no digital sensors, no external power needed. Now, some designs might add a light spring to kind of help things along, but fundamentally, this tool relies entirely on gravity and fluid pressure to do its job. So how does this actually look in motion? Well, when fluid moves in the intended forward direction, the pressure simply lifts the ball right up and off the seat. The fluid streams right past it, no problem. But the very instant that fluid tries to come back, the flow itself pushes the ball right back down onto the seat. The ball drops, makes contact with the ring, and boom, seals it completely shut. Now here's what's really fascinating: the sheer contrast in the physics at play. As a rule of thumb, a ball and seat valve needs almost zero forward pressure to open. We're talking about just a few pounds per square inch, or PSI, to lift that ball. But when the flow reverses, that exact same tiny marble can hold back thousands of PSI, literally thousands. And this is exactly why check valves are rated by their reverse working pressure, not their forward pressure. So what's the secret to holding back all that force? It actually comes down to some brilliant engineering on the seat itself. See, the seat isn't just a flat ring, it's heavily tapered. This means that when the perfectly round sphere lands on it, it touches along a perfect circular line. Any slight misalignment instantly self-corrects as the ball naturally rolls right into the center of that taper. And here is the genius part. The harder the back pressure pushes against that ball, the harder the ball is jammed onto that circular seat. It actually uses the enemy's strength to jam itself tighter. It is completely self-energizing. And this brilliantly illustrates why this exact valve is absolutely everywhere on a rig. It performs completely different yet entirely critical jobs across the whole industry. In the mud pump's fluid end, the suction and discharge valves use this principle to move heavy drilling mud. In a sucker rod pump, the standing and traveling valves are ball and seat, lifting every single barrel of oil up to the surface. Down at the bottom of the casing in a float shoe, it lets cement pump down but stops it from flowing right back up. And in a baler on a wire line, it drops open to scoop up debris and slams shot to trap the load. It's the exact same simple principle, doing 4 massive jobs. But like literally any mechanical device out there, it has a vulnerability. There's this silent killer in the oil field, and it's known as cutting. When you're pumping fluid that contains sand or grit, sometimes a tiny piece of that grit gets trapped right on that perfect circular sealing line between the ball and the seat. So when thousands of PSI of reverse pressure try to squeeze through that microscopic gap, the fluid jets across it like a high-pressure cutting torch. Very quickly, it carves a permanent groove right into the steel seat. And look, once that groove is cut, that valve is going to leak, period. It can never reseal itself. Which brings us to an absolutely crucial maintenance rule. You must always replace the ball and the seat together as a matched pair. Never, ever just swap one of them, because if you drop a brand new, perfectly round ball onto a worn, cut seat, it will never sit properly. The seal is compromised from day one. Let's play a little game here and put you in the shoes of a rig mechanic for a second. Imagine this scenario. You're monitoring a mud pump. It's turning at the exact same strokes per minute it always does, and the pressure looks completely normal. But you've quietly lost about 15% of your total fluid output. Nothing sounds broken, there are 0 alarms, so what is your very first suspect? Well, the answer? It's the valves. A quiet, gradual drop in volumetric efficiency, where the pump is doing the exact same amount of physical work but moving less fluid, almost always means that fluid is slipping backwards on every single stroke. You have a cut valve. The pump pushes the fluid forward, but because the ball can't seal against the damaged seat, a portion of that fluid just escapes right back to where it started. To really wrap your head around how this functions in the real world, let's look at something super relatable, a human heart valve. Your heart valves are simply one-way flaps. They let blood through on the pump stroke and slam shut on the backstroke, powered entirely by the flow of the blood itself, with no external electricity or motors. The ball and seat valve operates on the exact same logic. It is powered by the very fluid it is designed to control. And actually, the similarities to a heart don't even stop there. A mud pump's valves will often cycle around 120 times per minute. That is roughly the speed of a resting human heart rate. Except these steel valves have to maintain that exact rhythm for weeks on end, completely submerged in abrasive fluids. And exactly like a human heart valve, when they begin to wear out and leak, you often lose efficiency long before you ever hear a strange noise or see a catastrophic failure. All right, so let's bring this all together. The crucial takeaway from this explainer is that the ball and seat valve is a total masterclass in efficiency. It only has two working parts. The tapered seat brilliantly ensures the ball self-aligns every single time. It uses the system's own back pressure to force an even tighter seal. But you really have to watch out for sand cutting, which can silently destroy that seal. And when that happens, remember, you must always replace the ball and the seat together as a matched pair. It is just wild how an entire massive industrial operation can hinge on something so small. So I'm going to leave you with this thought. The next time you're looking at a complex system and you see flow traveling perfectly, obediently, in only one direction, will you picture the powerless, elegant steel marble making it all possible? Thanks so much for joining me for this explainer, and I'll catch you in the next one.